First of all, I'd like to thank the organizer for giving me an opportunity to talk here. 고맙습니다. So, title is convexity. Theorem for three tangled Hamiltonian torus action. Today, I'd like to talk about some generalization of Atiyah-Gilman-Stumber convexity theorem, and which is called the convexity theorem. The convexity theorem itself states that the image of the moment map of Hamiltonian torus action is convex, and is actually the convex hull of the image of the fixed point set. And there already exists some generalization of the theorem. Some generalizations. Today's purpose is to give a new generalization. Today, a new I'm going to give a new generalization. There already is some generalization, and so why do I have to consider a new generalization? So let me explain the motivation first. From a point of view of theoretical physics, some people may not understand the viewpoint in theoretical physics. So if you don't understand physics, then just forget about this motivation and just think my talk is going to be some generalization. So let m omega be a compact connected symplectic manifold. And Tm be m is now we assume m is 2m dimensional symplectic manifold, and Tm be m dimensional torus. So if this torus has a Hamiltonian effective Hamiltonian torus action on m to m, effective Hamiltonian action, then it is well known that the set of component functions of with the moment map then we can define the component functions of this map as a.
The dimension of the torus is half the dimension of the manifold.
Yes, so now we assume M is 2m dimensional. And
Toric case.
yes. Thank you very much. So then, the set of component functions of this moment map with Hamiltonian function is equals to mu1 defines an integrable system. Okay, that means these functions are Poisson commute. That means the Poisson bracket is vanish. And those functions are independent. So this is fine. This is a well-known fact from physics and symplectic geometry. But independence is defined by the point of the derivative of those component function. We can consider these guys. Then the definition of these functions are independent is the point of these one forms are independent is forms an open dense subset of the original manifold. That means more or less the independence of functions. So anyway, this is fine, but in the case of total lattice, it's also an integral system. We have extra functions which have special properties. So in the case of total lattice, there exists extra function, which is a function of M, which satisfy the following properties. If we define a map F by these extra functions nu and these original functions mu by component functions, say nu m nu 2 h1, which is equals to mu1. So we are now combining these functions to this form. Then this is a map from the original manifold to the 2m minus 1 dimensional Euclidean space. So now what's happened here? So such that means, so first these functions are Poisson commutative from the fact of this here. So this is commutative. But now these extra functions are also commutative with respect to Poisson bracket, and those at 2n minus 1's functions are independent again. This system is called, if there exists extra functions, that integral system is called super integral system, and this is an example of that integral system. So now, let me explain what the ingredients of this map. So we can sort of understand this is a moment map of one torus action, which is a kind of abelian moment map, and this is also considered as an abelian moment map. So this map, this full map, can be understood as this is composed of two abelian moment maps, and the image, this guy, can be understood as like the target space of this moment map, say Rm nu, plus the target space of first original moment map. And by the way, as a digression to the theoretical physics, this existence of these extra functions ensure that the equations of motion on total lattice is always periodic. I'm not going to explain here very much, but so in theoretical physics, superintegral system is kind of really nice class of integral systems.
With respect to Hamiltonian H?
Yes, this is the main Hamiltonian function. So anyway, so we've already know a moment map of torus action has convex properties. So now here comes a question. Now the question is.
You said that this one is this one has the super system. Then which one is periodic?
So we can consider equations of motion on the total lattice with respect to Hamiltonian function, this function. Then we can consider that equation is a physical motion on the total lattice, and the solution has to preserve these functions, the values of these functions, because they are Poisson commutes.
Could you explain the meaning of independence?
Oh, sorry. That is same to here. The points of the one forms of component functions forms an open-dense subset.
You mean
of
the collection of all 2n minus 1
Yes.
functions are
Yeah.
independent?
So the physical path is the fiber of this map.
Yeah.
Exactly.
Yeah. So because of this is just one dimension smaller than m, the fiber, which is a solution of equations of motion, has to be one-dimensional submanifold in general, and that's a periodic orbit.
In circle.
Yeah. So anyway, my interest is on convexity of this map. So can we state convexity of maps of this type? Of this type means constitute of two abelian moment maps. So the original moment map, this guys, has the image of this map is a convex and can be it is actually the convex hull of the image of fixed point set. So I expected, so this also can be understood as a moment map of torus action. So this map is not a moment map of a torus action, but almost looks like the moment map of torus actions. So I expected that this map, the image of this map, is convex and could be written by the convex hull of something. I think that was. Is there any questions? So, to state the convexity theorem, I mean the Atiyah-Gilman-Sternberg convexity theorem, which I'd like to generalize here, let me explain some basic stuffs. Hamiltonian actions and the convexity of convexity theorem. So let M omega be a compact connected symplectic manifold again. That means by the definition of symplectic manifold, the omega is a closed two-form which gives a non-degenerate pairing on each point of the manifold. On each point P, the symplectic form gives us bilinear, which is non-degenerate. This is just by definition. And this non-degeneracy, actually the definition of non-degeneracy is any dimension of Lie group and any
Smaller than 1 half, smaller than equal.
that could be fine. It's not related with so yeah. So this could be arbitrary compact Lie group, and the manifold also could be an arbitrary manifold. So let me explain this theorem by the previous example. So because CP2 is a co-adjoint orbit of SU3, and if we consider full symmetry of the co-adjoint orbit, the curve-on polytope is always just a point. Because the co-adjoint orbit always intersect with if we identified with co-adjoint orbit and adjoint orbit, the adjoint orbit is has intersect only finite point with the maxima, the Lie algebra of maxima torus, and because that has to be a convex polytope, then the intersection has to be just a point. So anyway, that's not interesting case. So
Could you say on the,
oh sorry.
so the two action on G and G star.
If we consider like compact Lie group, and if we consider that's a co-adjoint orbit, then
G star.
sorry.
Oh,
Sorry. Well, on a, let's see adjoint orbit. Then this guy has intersection with the Lie algebra of maxima torus with finitely many points. Sorry, I should explain something, but sorry. So this guy always into the Lie algebra of maxima torus. If we identified dual and original one, so sorry, it doesn't make sense. Sorry, so let me explain later. But so anyway, the full symmetry of co-adjoint orbit is not interesting. We can also see that situation by moment map can be given by just the inclusion of co-adjoint orbit to the dual Lie algebra. So it's not interesting map. So let me consider a subgroup action on CP2 between that maxima torus, which already discussed before, with G. Let us define this guy, this form, which is given by the form of the matrices in SU3, this type.
It's not so group for SU3.
Outside.
outside.
Right. Sorry. Thank you.
No, S is outside. S.
Oh, sorry.
And then S usually you just use.
Oh, right. Okay, so, yes. Well, I'm sorry, but let me change to the action of SU3. Yeah. Sorry, I'm sorry. Okay. It's not a big deal. So, anyway, so this forms, we have this form subgroup here, and if we identified the dual stuff and the original Lie algebras by G invariant inner product. The image, like before, we can obtain a moment map of this action from the moment map of the original action. And now, the intersection of the moment map. So now we consider G and to dual of G. G is this guy. And the intersect. So if we identified the dual and the original one, this positive Y chamber is of course in the Lie algebra of maximal torus. So first, let me think intersection of the image of this moment map and the Lie algebra of torus, maximal torus. Then the intersection can be is just this area, and the positive Y chamber is in this case can be given a half plane of this two-dimensional space. So by choosing a positive Y chamber, we can understand this area is a positive Y chamber. Then the intersection guy, this guy, is this segment. So, like we can see in this picture, I don't see for now any good, nice description of faces or vertices of that polytope. So, is there any questions? Okay. So anyway, here you can see the moment polytope of the maximal torus, and one place is the current polytope now. And for a new generalization, which I'm going to explain, I will compare with these two examples. Okay, so I think I should use here.
The image of the UG is the two segments?
No, the intersection of this image and the maximal, the Lie algebra of maximal torus is, yes, this segment, yes.
What is the lower half plane?
Why?
I don't know. What is it?
Sorry?
What's the lower image representing? Lower head plane?
This half plane?
Use a shaded plane.
Oh, this is a positive Y chamber, which I just choose one thing. Depending on the basis of root system, you can also choose here. It's not a big deal. It just depends on its choice. So, okay. Does it make sense for you? Okay. So here comes a new generalization. So by the way, sorry. Before discussing the new generalization, let me explain why do we need this new one again. So, like we can see, so this is current generalization, and it's kind of celebrated theorem. But the intersection, this intersection, which that theorem states its convexity, is actually included in the Lie algebra of maximal torus. But the importance of the existence of extra functions in the motivation part shows that the data of extra functions should be important. But here, we don't have any information for bigger space of bigger than the Lie algebra, because which is included in T. So, we should think we should extract the data of extra functions, which in that sense we can sort of expect the map capital F has its convexity in its full image, not the intersection. It may not be clear, so let me explain the new generalization. So before doing that, this generalization, the setup of this generalization may be a bit complicated, so please just be patient. Sorry about that. But so let T1 and T2 and T3 be maximal tori of the group G. And correspondingly, we write German T1 and German T2 and German T3 as their Lie algebras. Okay. Then we can define mu ij, which is a composition of the original moment map and the natural restriction map to the sum of the dual of the sum of these Lie algebras. So ij runs 1, 2, 3, of course. So this is moment map and this is restriction. Then here comes a theorem. First, assume for any I, j, k, which is equals to 1, 2, 3 as a set. That means I and j can't be equals, and similar to j and k and so on. For these ijk, we assume this condition. So ti is equals to the intersection of these three torus plus the commutator of tj and tk. We assume this condition for any ijk which runs the 1, 2, 3 set. I think this may look like very weird. But then, anyway, then we can state its convexity. The image of this composition map is convex and is actually a convex hull of the adjoint orbit of tk tk adjoint orbit of the image of the fixed point set. So this is kind of complicated condition, but for now anyway we can state its convexity. And again, this is because this is complicated. Let me explain this theorem by a continued example. Oh, sorry. By the way, I use tangled Hamiltonian torus action because of this condition. This may looks like T1 and T2 and T3 is like, yeah, I don't know how to say, but and to be a generalization of the convexity theorem, we have to recover the original one. But if we just choose T1 is equals to T2 is equals to T3, that 3 tori always satisfy this condition. So this actually recovers the original theorem. And the point here is because this maps M to this space, and since we chose T guys to be a maximal torus, so this is not an abelian subalgebra. It's kind of interesting. So let me explain by an example. Okay. So the precise form is not a big deal, but to see what happens, let me define T1 and T2 and T3 in the previous example. So our group is U3, and we chose T as a maximal torus, which is given by diagonal matrices. And now we are going to define another maximal torus. These spaces are always 0. T1 defined to be, so these variables, theta and theta runs all the real numbers. Sorry, I don't write such conditions here, but this is just actually the original algebra of the maximal tori, because this is given by diagonal matrices. And T2, the two-dimensional abelian subalgebra, which is given by eta minus eta. Similarly, eta and theta runs all the real numbers. And the third one can also be given by what's this? By the way, these I are irrelevant to the ijk here, which is just square root of -1. Sorry about that. So from this definition, we can see this part corresponds to the intersection part there, this part, and this part is generated by these guys. So eventually what happens here? course, because we know moment map of U3 reaction on CP2. Sorry, this M is no, sorry. Now we are choosing M as a complex projective plane CP2. Since we know the moment map, a moment map of U3 reaction on CP2, we can construct this map explicitly. And I'm not gonna write that map, but in the sum space, we can write a picture which illustrates these all three generalizations. So this cone is this is the image of mu12 of CP2, which is given by its interior points and the boundary, which can be called convex cone or something. And here, this triangle is the moment polytope of the diagonal torus, and this segment is Coulomb polytope. Like this. So I don't have much time. So, but in this picture, the plane, which looks like XY plane here, is T1, and this plane, which looks like YZ plane, is T2, and the intersection direction goes this way. So maybe this hat is actually its convexity, and this is okay, but because adjoint orbit is a infinite set, this image is not a polytope in general. So it may not be a big theorem, but it's kind of interesting because the image is still convex. And I'm going to stop here. Thank you very much.
Any question or comment?